choke valve is one of the most important but least studied components of the wellhead. It is also the most critical element of the flow line that directly impacts production and revenue.
In the oil and gas industry, choke valve design is governed by API 6A and 17D standards. Choke valves are used to control flow rate and pressure drops. Reducing the flow channel with an orifice accelerates fluids, sometimes to sonic speeds. For that reason, the design of a choke valve must consider the effects of erosion, high fluid velocity, and significant pressure changes. Choke valves are categorized by their application, including drilling, injection, and production. Drilling chokes are employed to control high pressure fluctuations during the well drilling process. Injection chokes are usually used to control flow rate and back pressure in the pipelines going into the injection wells, including gas and water injection systems. A production choke is typically used for well optimization or to reduce the wellhead pressure to a level that is safe for transportation. All choke valves face three main problems: erosion, hydrate formation or freezing, and flow controllability.
The flow rate is controlled by restricting the flow to a small opening or orifice. The degree and level of control depend on three main factors: choke trim design, actuator resolution, and measurement accuracy. Other factors include valve clogging and wear due to erosion and corrosion.
Let's discuss the flow characteristics of 4 types of choke valves. The needle and seat has a tapered lead on its stem to restrict the opening by closing the tapered seat. The throttling is achieved by rotating the handle on its rising stem.
Due to the tapered design of the needle, a small rotation of the stem handle can cause significant change to the orifice opening. This choke design doesn't provide a high degree of control. When the choke is open halfway, you experience full flow, losing most of your control. The multiple orifice valve design allows for proportional changes in the flow. This type is most applicable when the upstream and the downstream flow are controlled at fixed points. This is not the case in nature. As the well is unloaded, the upstream pressure comes down and the downstream pressure rises. In a refinery application, for example, the upstream pressure is typically fixed. The cage with internal plug and external sleeve choke valve designs are both characterized by equal percentages or modified parabolic control. They provide a gradual response in the lower portion of stem travel, delivering high level of initial control. This brings the well on stream. As the valve is open and the flow increases, this level of control is maintained throughout the stem travel, resulting in high turn-down ratio, high repeatability, and precise flow control.
This is imperative because a well-controlled flow allows you to ramp up your well slowly. A rapid well ramp-up can destabilize it, potentially causing a collapse and reducing well's productivity index. Avoiding damage to your most valuable asset, the reservoir, is crucial.
Masterflow's standard trim provides a high level of control over its life. The smaller lower ports provide the initial 15% of the control range, while the larger ports provide the valve's overall capacity. This results in equal percentage flow characteristic curve and high liquid pressure recovery factor. To compare valve capacities and to size valves for specific applications, several coefficients are used. The first one is a flow coefficient.
Flow capacity testing establishes a flow curve over the valve travel and provides a basis for comparing trim styles. Each valve type has a unique curve based on internal geometry.
A greater restriction provides better velocity management but lowers the flow capacity. When the seating area is close to the throttling area, the erosion issues may occur, as frequently happens with the needle and seat valve. Masterflow solved this issue by incorporating a dead band area in the design of the external sleeve and cage choke valve. The dead band ensures that the throttling area is far from the seat, resulting in an area of zero flow. Masterflow's custom trims could be designed for a specific pump curve, providing high loss coefficients at low flows and low loss coefficients at high flows. Custom trims allow to eliminate the need for parallel valve operation and therefore reduce maintenance while increasing reliability and controllability. In production, only inlet and outlet pressure values are measured. However, inside the valve at the throttling point, the pressure is much lower. This is designated as the vena contracta pressure. That brings us to another important factor of the choke valve selection process, the liquid pressure recovery. This is the ratio between the pressure drops and the difference between the upstream and the vena contracta pressures.
If the pressure in the choke falls below the vapor pressure of the liquid, cavitation may occur. When this happens, the pressure is greatly reduced in the valve. The susceptibility to cavitation is governed by the valve FL number, which determines how low the pressure can get inside the valve. In extreme cases, freezing of gas may occur in choke valve due to hydrate formation.
As you can see, the cage with the external sleeve design provides a higher FL over a wider range of valve openings. The higher FL number means a lower chance of cavitation and consequently, the risk of damage. For demanding applications with high pressure drops, two-stage trims could be used. They consist of concentric cages which handle pressure drops in stages, reducing pressure dip at the vena contracta. This results in better control over the cavitation and noise.
Masterflow's multi-stage trims are available in service-specific materials, including the proprietary 5CB tungsten carbide for higher erosion and corrosion resistance. Multi-stage trims can also be engineered to provide custom flow curves.
The effects of staging can be seen on these graphs. When more than two stages are needed, a labyrinth-style trim is employed. It features an internal plug and a labyrinth cage that allows a smooth transition between cage ports. Also, controls the velocity throughout the labyrinth. These trims are available for liquid, gas, and multi-phase applications. The trim cage is compression loaded
And constructed as a solid element of tungsten carbide
for durability and ease of service. The custom port designs are available to optimize performance depending on the fluid type and
gas-oil ratio.
This chart demonstrates a few possible flow control curves. However, Masterflow can provide almost any control characteristic to fit the needs. Masterflow's custom trim designs go through extensive CFD analysis where the control characteristics are evaluated, feeding the information back to the engineers. It's time to master the flow. Masterflow.